Hi guys, we're going to have a look at some applications, real life applications of functions in this segment. I've got three examples for you, so let's get started. In the first example, we're saying that the cost of a carpenter for home handyman services is $125 for up to the first hour and then $100 per hour for each subsequent hour. Find the function C being the cost function of x, which describes this method of payment, and sketch the graph of y equals c of x, where x is the time in hours for which the tradesman has worked. Now, after you've taken a moment to absorb that, and you're free to pause the video as necessary, let's make up what we think this function looks like. Well, I think it's a hybrid function, or a piecewise function as it's otherwise known. And firstly, I think that the cost is the flat rate of $125, where x is anywhere from 0 to 1 inclusive. So I think it's saying that the cost is equal to $125 flat rate for x being anywhere from 0, greater than 0, up to and including 1. Would you agree? I think so. And then, but what about after that? Have you got something for that? Well, I think what it is for each subsequent hour, it's the original $125 plus take 1 away from however many hours you've got, and multiply that by $100 for each subsequent hour apart from the first hour. Would you agree? Good on you. So we're both in agreement. So now let's sketch the graph. There's some scales. I've got C dollars here and I've got X hours down there. So let's go with it. There it is. There's the first hour, the flat rate of $125, and then we've got a gradient of $100 per hour going up there, so that after 2 hours he would have spent, or we would have spent on the tradesman, $125 plus 1 hour at $100, which should make a total of $225. You get it? Okay, beautiful. Make sure your graph is labelled well and there's a scale on each axis, and everything will be great. Now, in example 2, we've got a rectangular pizza box is to be made from a piece of cardboard as shown, or as I will show you in a moment, where the height of the box is to be x centimetres. 4 squares of side length x are to be cut from the corners to enable the box to be constructed by folding up the flaps. Now we're to find a function for the volume of the box v, cubic centimetres in terms of x, and we're to find the domain for the function. Okay, let me show you a picture. There it is now. Okay, we've got 30 by 20 here. We've got 30 by 22 this away, and here is the little square of dimensions x by x, which we cut out of each corner so that we then can fold along these dotted lines to actually make a box. You see? Get it? Alright, so let's see, we've got to come up with a function v for the box in terms of x. Now you might like to pause the video for a moment and come up with that yourself and see whether you agree with me. So here it comes. I think v is the length, which is 30 minus 2x, times the width, which is 22 minus 2x, times the height, which is x. Now if you take 2 out of here as a common factor and 2 out of here as a common factor, you'll get this. Okay, really good. Now we've got to talk about the domain. Now, for the domain, guys and gals, the length, the width, and the height all have to be greater than 0, otherwise we haven't got a box. So that's the way I see it, and I'm sure you would agree. So therefore we're saying that 30 minus 2x has to be greater than 0. Also we're saying that 22 minus 2x has to be greater than 0, and of course x has to be greater than 0. So let's just simplify that down a little bit in the next line. This one distills down to x being less than 15. This one, we get x is less than 11. Now, both of those have got to be working at the same time. Both of them have got to be satisfied. In fact, this one has to be satisfied. So all three of them have got to be satisfied at the same time. So what do you think? How do we express that? Well, here it comes there. I think this means that x has got to be greater than 0, which is this one. But then if we say that x is less than 11, it satisfies this one and that one at the same time. So therefore, that's my answer. X is from 0, x is greater than 0, but at the same time less than 11. Okay? Good on you. Now, in this third example of 3, we've got a cylinder which fits inside an inverted right cone, so that the top of the cylinder is exactly level with the base of the cone, as I'll show you in a moment. The cone has a radius of 10 centimetres and a vertical height of 15 centimetres. The cylinder has a radius of r and a height of h. Now we've got to find the volume of the cylinder in terms of r and find the domain of v, the volume. Okay, now I'll just reveal my diagram, and then you might like to pause the video and have a go at it, and then we can compare notes. Here comes the diagram. Okay, see you in a moment. Alright, now, this question is all about similar triangles. It looks jolly confounding when you see it like this, but it's not that difficult when you draw these similar triangles over here, which represents this situation on the left. Now, let's just play it out for you. We've got 15 centimetres down this way, which is the height of the right cone. We've got 10 centimetres over this way, which is the radius of the right cone. Okay? Now, what I've also drawn in that diagram over there, this little triangle here represents this triangle here. Okay? This triangle here. Now, this length here is 10 minus r. So I've written it over there, 10 minus r. You think about that. Do you agree with me? Yes, because the whole thing is 10 and we're subtracting r from it. So that's 10 minus r. And the height here is the same as the height here, which is the height of the cylinder, which of course is h. Now, why did I do that? Why did I do that drawing? Well, the reason I did it, guys, is because I have to get a connection between r and h. Because if you start fiddling with the radius of this cylinder so as to keep the height of the cylinder flush, the top of the cylinder, I mean, if you start fiddling with this cylinder, bearing in mind that the top of the cylinder has to remain level with the base of the inverted cone, if you change the radius of the cylinder, if you change r, then h is going to have to change to accommodate so that the shape inside the right cone is preserved and that the cylinder stays, so that the top of the cylinder stays exactly level with the base of the cone. Okay, so r and h both change, and they have an interrelationship with each other. See, so I've got to get a connection between r and h if I'm to express the volume V just in terms of r alone. Okay, this is the crux of this question. Alright? Now let's go over here and do some similar triangle maths, and we can see that by similar triangles, we've got this little triangle here is exactly similar to the big one, because you can see that they share a common angle here, and they also have a right angle here and here, and therefore the third respective angles must be equal, so they're A, angle, 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 similar triangles, yes? Now you won't have to prove that in an exam setting, but you have to realise it, okay? So therefore we can say that 10 minus r over h is equal to 10 over 15, which is the same as 2 over 3. Now I'm going to do some cross multiplying, and I'm going to try and express h in terms of r, okay? So I can eliminate h from my formula for the volume of the cylinder, okay? Alright, now that's cross multiplying. Yes. Does that make sense to you? Yes, it does, to me anyway. So therefore I'm going to say that H is therefore... So therefore I can say that 10 minus R is the same as 2H over 3, and therefore H would be 3 over 2 times 10 minus R. Jolly good show. Now that's a big step forward. We're going to go over to the next screen now and have a look and do a recap. Okay, we've got that. Now we're going to proceed with the volume for the cylinder. V is pi r squared h. Let's substitute for h from this formula here, and we get that. Okay, now, therefore, this is our formula for the volume. Okay, just cleaned up a little bit. There it is. Do you like it? It's pretty nice. Now we've got to do the old domain trick here. For the domain of V, the volume of the cylinder, ladies and gentlemen, we would know that R has to be greater than 0, and also H has to be greater than 0 at the same time. Otherwise, we don't have a cylinder, do we? No. Alright, so if H is greater than 0, then we're saying because H is this thing, then this thing has to be greater than 0, and we can easily solve that for R. Yes, it means that 10 minus R is greater than 0, and therefore R is less than 10. Okay, now we also set up here that R has to be greater than 0, so therefore we've got our constraint on R, and we're saying that R is between 0 and 10. Greater than 0 and at the same time less than 10. There you go. That's the end. And the end is your friend. We'll see you soon.